Hello, grade 10s, and welcome to your next AP Maths lesson. I think you're going to enjoy this concept because it's straightforward. It's not actually AP Maths today. This is normal grade 10 work, but we haven't yet covered this chapter. And so before we can continue with our AP Maths work, you need to know these concepts. So today we're actually just doing simultaneous equations from our grade 10 textbook, and you will very likely see this lesson repeated a little later on in the term. Right, before we learn any new information, I'd like you to just consider what you already know. Imagine you were given two straight lines on the Cartesian plane, a blue one and a green one with their relevant formulae. The green straight line is y equals x plus 1. You can see that that's a straight line equation because x is raised to the power of an invisible 1. It's not a parabola or a hyperbola like the other functions you've dealt with. And you can see that it's got a positive gradient and its y-intercept would happen there at 1. We don't need that for now. We're just exploring these two straight lines. Then if you have a look at the blue straight line, you can see that negative x means that blue would have a negative gradient and its y-intercept would happen up there at positive 3. Now, what if I asked you to go and find that point of intersection, that yellow bullet where the two graphs intersect can be found, I know you know this already, by making the two equations equal to each other. So I've taken the blue equation, negative x plus 3, and I've made it equal to the green equation, which is positive x plus 1. If you chuck the negative x over the equal sign and you chuck the 1 over the equal sign and solve for x, you will get that 2 equals 2x and x equals 1. Right, that's easy peasy. So we know that on the x-axis, when x equals 1, we've got the point of intersection. But the point of intersection is a coordinate at the end of the day, and a coordinate has an x value and a y value. So now that we've found x equal 1, we still need to find its corresponding y value. So what you need to do is merely substitute x equals 1 into any one of the equations. I've substituted x equals 1 into the green equation because I always avoid negatives. So y equals x plus 1. So if I substitute 1 in the place of x, I will get y equals 1 plus 1, which will give me 2. And there you can see on the sketch when y equals 2 and x equals 1, we've got the point of intersection. So remember that an x and a y value makes up a point of intersection. And this whole concept is the introduction to what we call simultaneous equations. Simultaneous equations involve more than one equation at a time, and because more than one equation is involved, more than one variable is involved. Up until this stage, you have only solved equations with one variable. These equations have even been quite complex, so like x squared minus 5x plus 3 minus 2x equals 0, and then you are expected to solve x. But now you are going to be given simple, straightforward equations, but you'll be given two of these equations and you'll be solving for two variables. Note that for simultaneous equations, the number of variables you have to solve for must always equal the number of equations that have been given to you. In this picture, we have been given two equations, a green one and a blue one. But in the future, you may be given equations and you won't be given the picture or the graphs of those equations, and you will still be able to solve for the variables. And that's what we're going to do in the very next example. Here we are given two equations that we are expected to solve simultaneously. Now, if you have a careful look at each of these equations, you'll see that there are two equations and two variables. So we will be able to solve for these equations because the number of variables that we need to solve for matches the number of equations that we need to find. That the number of variables we need to find matches the number of equations we've been given. So if you had to find 3 variables, an x, a y, and a z, you would then have to be given a third equation. But you don't have to worry about that because we're not going to deal with that this year at all. Right, so if you have a look at the form of these equations, don't you agree that if you made y the subject of the formula for both of these equations, we'd actually be dealing with 2 straight lines? And if you are solving 2 straight lines simultaneously, you are merely finding the point of intersection of those 2 lines. But in the method I'm going to show you now, I'm going to avoid needing to make y the subject of the formula in both, like we did in the previous slide. If you have a look, when we made x plus 1 and negative x plus 3 equal to each other, we could do that straight up because y was already the subject of the formula in the previous slide. Here, y is not the subject of the formula in either one of these equations, but knowing that you could make y the subject of the formula must make you realize that these are in fact 2 straight lines and you could solve their points of intersection. However, we don't need to make y the subject of the formula. We can choose any variable to make the subject of the formula. So first things first, I'm going to just call these equations number 1 and number 2, so that when I'm writing down my calculations, I can write down which equation I'm working with so as to avoid confusion. My eye is drawn to equation 2. Merely because that variable x has no coefficient. Well, it has a coefficient which is 1. So if I work with that equation first and I make x the subject of the formula, all I need to do is kick over negative x to the right hand side of the equal sign, and now I have a wonderful new outfit for x. I have got x all by itself, which means I have something that is equal to x, and that something is 3y minus 5. So I like to call this another appearance of x. It's x in disguise. So wherever you may see an x, we can actually replace it with what x is equal to. And so in equation 1, we see that we have a 3x plus 2y minus 29 equals 0. So why don't we work with equation 1 and take what x is equal to, take x's disguise, x's new outfit, 3y minus 5, and substitute it into equation 1. So wherever I see an x, I can now replace it with 3y minus 5. Now this is a magical move because look at this very last thing I've written down. I only have y's in this equation. So we can solve for y as we normally would in any other ordinary linear equation. Distribute your 3 into the brackets and add your like terms, kick over the constant, and you'll get 11y equals 44. Divide by 11 on both sides, and we get y equals 4. How easy is that? Now remember that if we are solving simultaneous equations, the number of variables we're solving for matches the number of equations we are given. We have been given 2 equations over here, yet we've only found a value for y. So we actually still need to find a value for x. Remember, a point of intersection is a coordinate, and a coordinate has an x value and a y value. So let's use y equals 4 to find its corresponding x value by substituting y equals 4 into any equation that we've been given, either 1 or 2. So I'm using equation 1, 3x plus 2y minus 29 equals 4, but instead of writing y, I'm replacing y with its value of 4. I then simplify, and I've substituted that into equation 1. You could have replaced the y in equation 2 with number 4, and you would get the exact same answer. So here, once I simplify or collect my like terms and kick over the negative 21 to the other side of the equal sign, you'll see that 3x is positive 21, and you divide by 3 on both sides to get x equals 7. Aha! Now I have the values of 2 variables, so I've reached the end because I was given 2 equations. Once again, remember that we've actually just solved for a point of intersection. So if we had to write down the coordinates of that point, we would write down x first and then y, which would give us 7 and then 4. I know this work seems to be all over the show, but I'm sure if you rewind and watch this slideshow again, you'll be able to tackle today's homework. On the next slide, you will see a summary of the steps involved in solving simultaneous linear equations. So you can read through and jot down those steps and then go on to today's exercise. Enjoy.